So in each of these examples, we had two or more random variables that had a joint distribution, and we wanted to know the characteristics of their joint distribution in order to answer the questions that we were interested in. Okay, so how do we do this? Well, I told you already the workhorse model to do this is the linear model. So let me introduce the linear model bivariate style. We'll sort of generalize that later. And let me just sort of go through and define what the things in this linear model are. Okay, and then we'll talk about sort of properties of it, and we'll talk about how to estimate the parameters in it and so forth. Okay, well, the linear model is a model that sort of establishes a relationship between two random variables on which we have repeated observations. So these are y and x, okay? And a third random variable, oh, sorry, I'll get to the third random variable in a second. So y is what we call the dependent variable, okay? Sometimes you will hear that referred to as the explained variable or the regressand. I would say hardly ever do I hear those terms, but those are both, you know, sort of legitimate terms, I guess, for the dependent variable. And then the x variable is typically called the regressor or explanatory variable, or sometimes called the independent variable. So even though like regressor and regressand seem to go together, or independent variable and dependent variable seem to go together, that's not the way these terms are used. Typically, we refer to the y variable as the dependent variable, and typically you'll refer to the x variable as either the regressor or the explanatory variable. Okay? And there are some reasons for that, but this is just basically what people do, just so you're familiar with the terms. And then we have a third random variable thrown into the mix, an unobserved random variable, and we call that the error. Okay? We also have two parameters in this model, or at least two obvious parameters. We have another one that we'll talk about later. And these are parameters we want to estimate. And we call these the regression coefficients. Okay, so what does this model do? It allows us to consider the mean of a random variable y as a function of another random variable x. And if we obtain estimates for beta naught and beta 1, then we have an estimated conditional mean function for y. So let's add some basic assumptions, and then we will get to something called the classical linear regression model when we sort of pile on a few more assumptions. Okay, first of all, let's assume that our two random variables on the right side are uncorrelated. Okay, so x sub I and epsilon sub I are uncorrelated random variables. Let's assume that what this second assumption called identification means is just basically that we have some variation in our x variable. I'm going to show you a picture illustrating this in a second. But basically that just means that the x variable is not, the sort of repeated observations on the x variable are not all on the same point. Okay? We're going to assume that the expectation of our error is equal to 0. We'll assume a homoscedasticity, which means that the expectation of our error squared is equal to sigma squared for all I. And we're going to also assume that we do not have serial correlation. So in particular, the expectation of epsilon I, epsilon j is equal to 0 for all I and j. Okay? So let me talk about each one of these in turn and show you some pictures so you sort of understand exactly what the meat of these assumptions is. Okay. Oh, I should, a couple notes. We sometimes impose an alternate assumption to 1 for our convenience. And that's, sometimes we assume that instead of x being a random variable, xi being a random variable, we assume that xi's are fixed in repeated samples or non-stochastic. This makes some of the proofs easier. Sometimes we do it for convenience. The results essentially go through without that assumption. But we'll sort of go back and forth between that. And then the other note is that assumptions, we had the 3 different assumptions on the error term, and all of those assumptions could be subsumed under one stronger assumption, that the epsilons are IID normal 0 sigma squared. Okay? So sometimes, especially when we talk about inference, we'll impose that assumption. Again, that assumption is not necessary for almost anything that we do in linear regression, but sometimes it's sort of convenient. It makes the proofs easier and sort of more elegant, I guess.